Yeah, there you go. I like that one a lot. All right. So otherwise, I don't think there's too many other updates to give. I think that's basically it. So I think we can go ahead. So I do want to recap from last week. You know, we talked about 2D motion. I said it a bajillion times, but it's always good for me to say it a bajillion times more. Remember, literally the only difference between 1D and 2D is you have a second dimension, and so you have to split everything in X and Y. That's it. That's the only difference. 1D motion, the equations, it's the exact same equations. You just have the pleasure of doing it twice now. Also, we did a bunch of projectile motion. Well, I say a bunch. We did I think one, and it took maybe two. They take a bit. Look at all this writing. I crammed it into too tight of a space. This one's a little nicer. Projectile motion problems. Once you've done a couple of them, once you can do a couple of them, the rest will start going really smooth. But make certain you spend that time sooner than later, making certain you can do a couple of them. They're classic. And they can be applied to a bunch of situations and all that kind of jazz. But there was one problem I didn't get to that I highly recommend. This is the last one, which is the most challenging one, but it's a really interesting one. I mentioned it at the very beginning of the PowerPoint, and so now I'm mentioning it at the end. You have someone skiing down the slope, and there's an 80-meter gap in front of them. And to cross it, they have 100 meters before kind of the bottom part. So basically the question is, will they make it? Will they make it across that gap? And it's a really interesting question because remember one of the major criteria, there was a few steps to solving there's a few tips I gave you all. So split everything in X and Y, and the next one, determine what limits the time. Is it the Y coordinate or the X coordinate? Is it hitting a wall or is it hitting a floor? But in this problem, you don't actually know which is going to happen. You don't know which one's going to happen. Are they going to hit the wall or are they going to hit the floor? And so it's an interesting problem because you have to actually determine which one is the limiting by doing the math. And I'll kind of leave that for you all. So really, it's not that terrible. The fact that they're going downward, all that means is that their initial velocity in the Y direction is negative. The equations all still work the same. It's nothing absolutely great. This problem is very similar, as weird as it sounds, to a ball getting launched upwards at some angle. Let me, I guess, from some kind of surface. It's like the opposite of that problem, but all the equations are exactly the same. So I highly, highly recommend you all try this problem. It's a really good problem. It really does test, do you know what's going on? It has all the pieces in it. That's why I like it. So, anyway, there's that. Wanted to mention it to you all. Just because I didn't do it doesn't mean it's not important. It just means we didn't have time for it. But I talked about it, so that's what matters. All right, cool. Moving on to today's stuff. So today's stuff is, as I mentioned, circular motion and Newton's laws. And again, it's going to be, circular motion is actually fairly straightforward. We are going to talk about, the reason circular motion is kind of tacked on here is because there's a force, there's something called centripetal force. And that has to do with things going in a circle. So first we're going to talk about things going in a circle. So then when we get to Newton's laws and forces, we can actually talk about centripetal force. So that's why it's here. And we've talked about linear motion, so circular motion is kind of a expected next step. Lots of things travel in circles, y'all. Lots of things. There's a penguin. A lot more than you might realize. Wheels obviously spin in circles. But if you think within a car, pulleys, drivetrains, your chair spins in a circle. You're on an Earth, that's spinning in a circle. The Earth is orbiting a sun, that's going in a circle. A lot more things go in circles than you might realize. So, we're going to talk about position, velocity, and acceleration, variables we talked about for things going in a circle. We're going to talk about centripetal and tangential acceleration. They are different. We're going to then get into forces. What is a force? That's really important. And then how do forces affect objects? And then free body diagrams, which is a buzzword. If you've ever taken a physics class or anyone that's talked to you for physics about forces, free body diagram comes up. Very, very important. Remember, step 0 in any problem is drawing a picture. This is me teaching you how to draw a picture for forces. It's really easy, but it's really important. If your picture is bad, you will solve the problem incorrectly. Like that's pretty much a guarantee. If you can't draw a picture of the problem, that means you probably don't actually understand what's going on in the problem. And so that's why that's a good step to do. If you can't do that step, it doesn't matter what math you can do. It's not going to work out well for you. All right, circular motion. Look at, wow, circles. Things travel in circles, so many things. Wheels are very important to us. Being able to transmit linear motion into rotational motion and vice versa is invaluable. Like, can't stress that enough. Yeah, I'm not going to get too much. We'll leave it at that. I was like, how much do I want to talk about there? All right. There are some conditions. So we are talking about uniform circular motion. And anytime I introduce vocab words, I have to define exactly what that means. So like, remember in kinematics, the only criteria was acceleration was constant. When it comes to the circular motion problems, there's also some criteria that will always be true. The tangential speed is constant. We'll talk about what that is, but for now, I'm just kind of going through these. Something moving in a circle with constant speed is accelerated towards the center of the circle at all times. We're going to see that later. And then the tangential acceleration is 0 at all times in uniform circular motion. So what does this mean? It's not... Number 3 and 1 are basically saying the same thing. It's not accelerating. It's not spinning faster and faster and faster and faster. We will do those problems at the end of the semester. For now, we're doing the simplest case. I have something spinning at a constant rate. That's, long story short, that's all this is saying. Your wheel, whatever it is spinning at a constant rate. It is not spinning faster. It is not spinning. It is not speed up. It does not slow down. And we don't care what it's doing linearly. We're just worried about the circle. Something spinning. The simplest case, something spinning at a constant velocity. All right. Clockwise and counterclockwise. It sounds stupid, but how do you define which way something is spinning? This is the terminology we use. Clockwise and counterclockwise. It's very handy for those that know analog clocks. If we all switch to digital one day, this will be a relic of the past, and people will get to say, back in my day, we had analog clocks, and they spun in circles. Funny, it will happen. At some point, maybe in your lifetime, you will encounter someone who has never seen a clock like this. I can almost digital, I don't know. We'll see. I would bet on that. Just because, look in this room. There's no analog clocks in this room. Unless you're wearing one on your wrist. So anyway, if vast majority of you all, and who knows, maybe there's someone in this room. I doubt it, but if that's you, that's okay. Counterclockwise and clockwise are as follows. It's kind of hard to do. Clockwise is clockwise, counterclock. It's the way a clock goes. You'll hopefully know that. But the reason that this is important, we can't just say it's going to the right, because when you're going clockwise, at the top you're going to the right, but at the bottom you're going to the left. That's why we have to use this kind of terminology. You can't just say up, down, left, right, because that changes no matter where depending on where you're at. So clockwise and counterclockwise are bread and butter. That's what I will use to describe how something is rotating. As silly as it sounds. If you get really fancy in later physics classes, you might say, gosh, I don't even know, like positive state? Yeah, I don't know. That's just I don't even know if there is a fancier way of saying that. So we'll leave it at that. Okay. Radians. Again, this is just a bunch of vocab stuff to make certain we're on the same page. We've already talked about this. And I've already mentioned some of these points, but just to reiterate, you can measure angle and degrees in radians. I think there's also another way. There's a third way. I don't remember what it's called. Huh? I think it's on your all's calculator, actually. But it never gets used. I'm not going to worry about it too much, but while I'm jabbering, I'll grab my calculator and see if mine has that mode. Anyway, radians is superior mathematically. I'm going to show you all today why that is. I mentioned it in the past. Radians actually mean something. The spoiler is there's 2 pi radians in a circle. That's how you get the circumference of a circle. So it actually has like a physical connection to it. Whereas degrees, I learned in this class, came from, I guess, the number of days in a year, something like that. 360-ish days in a year. So that was interesting. I learned something new. But yeah, it doesn't actually, like, we just kind of decided to make up those. But degrees are nicer because if I told you 30 degrees, the vast majority, if not everyone, can vision what 30 degrees is. If I told you pi over 3, you would have to, like, picture the unit circle in your brain. And even pi over 3, I believe, is 60 degrees. Yeah, it's not even 30 degrees. So, see, pi over 6 is 30 degrees. You basically have to convert it to degrees in your head to understand it. Anyway, but we're going to be using radians here. So this is one of the cases where radians will pop up, kind of, sort of. We're going to use it a tiny, 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 tiny bit here. And then at the end of the semester, we'll use it more. Cool. All right, great. Test your radian knowledge. I'm going to give you all 30 seconds. How many radians is 45 degrees? This is just to prove a point. How many radians is it? You got 15 more seconds. Oh man, you have to shoot me an email. Yeah, don't forget about your subscriptions. We're at the phase where they will expire. If that happens, I have the pleasure of you sending me an email and I'll give you some points for it. We got a long class, so try to, pay for it sometime during this class. And is my alarm going off yet? No, we got a few more breaks. 10? Oh my goodness, alright. Yeah, alright. I'll give you all till a minute. I'll cut it. Oh, iClicker stuff. It's the first question. That's fair. That's fair. I'll wait for that. Is it working? That's fine. If at any point your iClicker stuff doesn't work, just shoot me an email. I'm not nitpicky on this stuff. I'll generally give you all the points for it. I recognize technology is finicky. Alright, so I'm going to close this out. I'll give you the points for it. Just shoot me an email. We'll close it out in 5, 4, 3, 2, 1. Alright, how we do? Ah, so good. Look at y'all. Great job. It is pi over 4. Wow. Alright, so great. We know what radians is. I fully expected that, but good to just remember that. Okay, converting from degrees to radians, fairly straightforward. You just do a ratio problem. So however many radians you have over 2, this is just a ratio setup. This is basically how you convert from anything to anything. There's 360 degrees in a circle. There's 2 pi radians in a circle. So you just set those 2 ratios equal to each other, and then you can kind of rearrange to get what you need. So, if we do the last problem, if you have 45 degrees out of 360, the question is how many radians out of 2 pi is that? You just multiply the 2 pi over into that. That's the unit conversion if you ever have to do it manually. Alternatively, you have a calculator that could probably do it for you. It has degrees mode and radians mode. There's probably some way to make it work. Okay. Why use radians? Oh, what a good question I've asked myself. All right, so this is the reason radians are superior. So the circumference of a circle is the 2 pi r. So circumference is 2 pi r. But what's crazy that you might not have realized is that applies to literally any angle. If you want to find any arc length. So a circumference is the entire circle, but say you want half the circle. You just multiply r times the radians for half a circle, which is pi. So if you want the length of half of a circle, it's r times pi. You want it for a quarter of a circle, it's r times pi over 2. You want it for some arbitrary angle, let's say pi over 6, r times pi over 6, and it gives you the length of that arc. Kind of nifty. It's so simple. And if you kind of look at the circumference, it's like, oh, okay, that kind of makes sense because it's just a percentage of that, basically. So it's a really, really simple equation if you want to find the length of any arc. You just multiply the radians by the radius and done. That's it. Super easy. It's great. It makes sense when you think about it, but you might not have thought about it before. I hadn't before I took physics and things like that. So you can use this for things, if you have a circle or if you have something in the distance that's kind of like this big, and you're like, man, how big is it? If you can kind of figure out how far away it is, and you know your angle, you literally just multiply those. But it has to be in radians. It has to be in radians. Now, your calculator does not have to be in radian mode for this to work. You just type in the radians. You just literally type the angle in. If the angle's pi, put pi. If the angle's pi over 2, put pi over 2. If you try to use this equation with the radius times 30 degrees, it gives you some nonsense. That won't be anything. So, ta-da! This is why radians is useful. This point and this exemplifies why radians are great. Except they use pi, which is a crazy number. All right, cool. Try it out. Try out the equation. And I always forget is it S? I always forget the symbol for arc length because it doesn't get used that often. Yeah, there is. I'll even write the equation for you all. S equals R theta. So is the answer 2R, 2 pi R, pi R, 360R, or 180R? Only one of those is right. Circumference. Oh. Yeah. So the whole point of this is to show, let's take the extreme case. Let's make an entire circle. What's the angle for the entire circle? And the radius of the... Well, there you go. Literally, that's where the equation for the circumference comes from. Okay. Or vice versa. Everything worked out. All right, we'll go for 10 more seconds. It's a fairly quick problem. Basically, the question is, what's the angle? All right, we'll close it out in 5, 4, 3, 2, 1. And ta-da! All right. So S is the symbol for arc length. I have no idea why S is the symbol for arc length. If anyone knows, feel free to let me know because I have no idea. Some variables are nice. R for radius, V for velocity, F for force, and then there's other weird ones like I guess T, capital T for period. Oh, yeah. That one I can justify. Q for charge. Oh, yeah. I for current. They're not things that my 3-year-old would say that makes sense, and therefore probably most people wouldn't say that makes sense. Current does not start with the letter. Okay, my 2, 3. She's not 3. She doesn't know that current starts with the letter I. She's not that smart. Or that any word starts with any letter. We're working on it. Yeah. There's some variables that just don't work out that way. All right, but y'all did a great job. It is pi over r, pi r, not pi over r, pi r. All right, and my alarm is going off because it is our favorite time. Time to do UCF here. So let me open it up. Yeah, get your phones to the thing. We'll still do the attendance stuff. So the points are being in there. So the way, if you haven't figured it out, the way that the attendance core grade is conducted is it's literally out of 100 points, and then as I do more attendance sessions, each class's percentage of that just decreases. Let's say I take attendance 10 times, then each attendance is worth 10 points. If I take it 20 times, each attendance is worth 5 points. When it comes to attendance, I've told you all I will excuse 4 of them. 4 of them means 4 class sessions. 4 class sessions. I have to do that manually, which means that will not happen except like around the tests. I'll do it manually like around the tests and things like that. But I am not going to do that every single week because that's a lot of work for very little gain. I have to download this as a big old CSV file. I then have to do some Excel wizardry. Yeah, I'm not going to do that every week. So heads up, that is still a policy that's in effect, but it will not reflect in the grades until I do it manually. Look at it go. Oh, and the people online. I wonder if it works after them. It's too late already. I have no idea. They got it to see it for like a handful of seconds. I don't know exactly how. I know, so as far as I'm aware, this thing, it has to be two ones after each other. I don't know if they're time stamped as well. I hope they are. They are. Do you think so?
When you scan it, it says like what date and what time.
Oh, nice. I really love that. I was like, it's really clever that UCF designed this way. I think it's really clever. As always, our wonderful undergrad LA Leo will go around and help anyone whose technology hates them. It's not personal yet. AI will take over one day, then it'll be personal. We're not there yet. Yeah. Yep. I'll excuse 8. Yeah, 4 classes. If I do it 2 per class. Yeah.
So like if you work your computer,
I'm not gonna. Yeah, I am not gonna go through and determine. I will excuse 8. I will excuse 4 classes worth, which will be 8 total.
Okay, I agree.
It's to account for any insanities. Alright, I don't see any phones up in the air, so we're gonna say that that's probably pretty good. So I'll actually remember to close this. And then I'll jump here. And then I'll hit slideshow, and then I'll click more buttons.
Anyone else before we go back?
Ooh, what courtesy. Alright.
I guess not.
At this point, I shouldn't get any emails then, right? That's how that works. Alright. What a challenging question. What if it's a full circle? Whoa. You got 30 seconds. Basically, it's just to see if your brains exists. These questions serve the dual purpose of just like letting you all use your brain and helping you stay a bit more mentally aware. Not making it so I have to talk the entire time. All right, closing out in 5, 4, 3, 2. Oh no. On your laptop? Hotspot. That's fine. Just shoot me an email. Yeah, if it's one question, it's easy enough. 3, 2, 1. All right, make me. Oh, look at that. We got the hundo. Good job, everyone. Oh, I always love to see it. 2 pi r. It's ta-da. You derived. Well, you know, it's which came first, chicken or egg situation. Did the circumference equation come first, or did the other one come first? You can. What's really cool about this equation is it's literally something that you can take from measurements. This is not an equation that's derived from anything. This is an equation that's measured, observed. Take a circle, get a piece of string, measure the circumference of the circle, and then just divide it by the radius, and you calculate 2 pi. The number pi is measured from reality, it's not derived from anything. And then you can prove this equation. Measure half the arc length, divide it by the radius. Oh, you get pi. Do a quarter of it. So this is where, in physics, the stuff I'm teaching you, we start with observations of reality, and we make equations from those, and then we'll use those equations in clever ways to make new equations. But we start with, here's how reality works. Whether you like it or not, this is what we can observe, this is what we can tell, and we make equations from that. Remember, we do not get to decide we don't get to decide the rules of the universe. We just get to measure them and then like write them down. That is physics. We are not deciding how the world works, we are just measuring how the world works. It's a really important distinction that people sometimes get mixed up on. Physicists aren't deciding the rules of the universe. We're just discovering them. 2 different things. In my opinion, that makes it so beautiful. There is like a right answer. And all we can do is say that we're probably pretty close because if we keep repeating experiments, our predictions match our expectations. And you make predictions based on equations and things like that. So, anyway, cool stuff. All right, velocity. All right, who's shining? All right, you're going to completely take the floor here, so I'm going to show him tangential velocity. Prepare him for it. All right, tangential velocity. He's going to give you, and I'll put up the slide, but if I put that up, it's going to be, everyone will be staring at that instead. Take him away, Leo.
This is not wanting to work. Okay.
Yeah.
I turned off.
And I can crank it.
Okay, so basically, we have something spinning. I'll do it here just in case. And it's proposed everyone moves out of the way.
Yeah.
And the question we're asking is what happens when I just let it go? And some people may think it'll like spin in a circle, but if I do let it go, it goes, you can't see it well, but it will go just in a straight line. I release a diagonal there. But contrary to what you might think, if you're spinning it, you let it go, it'll continue in the straight line, and that's your tangential velocity. Which means basically you have a velocity as you're going around, and if you stop this tension here, it'll just continue in the way it was gone. If that makes sense.
Yeah. Great. Thank you, Leo. Oh, so cool. So, you test this for yourself, y'all. The word tangential you've probably seen before. It means a line that intersects something at a single point. Ta-da! There's a slide for it. The long and short of it is tangential velocity is a straight line tangent to the circle. Wherever you're at. And we are going to practice this because some people that's going to like immediately make sense. A lot of other people it's not. There's a lot of misconceptions people develop with these things. With tangential velocity. The thing that I really want to point out, it's a straight line. It is a straight line. If you draw tangential velocity as a curved line, it's wrong. Tangential velocity is a velocity tangent to that spot. So if I said, what's the tangential velocity at this spot for something going counterclockwise? It's that arrow I drew. And you can test this for yourself. You can swing something in a circle and let it go. Now, technically, gravity is going to affect it, so it's going to do a parabolic arc, because of gravity. But just isolate gravity. When you release it so it's going like straight up. And it will go straight up. It will not swing in a circle and keep going in the path. I mean, in the way to think about that, why would it arc? If you point something straight up, why the heck would it start moving left or right when you let it go? There's nothing pushing it left or right once you let it go. It doesn't remember that it was going in a circle. It doesn't have any memory associated with its past movements. All it knows is at that moment, what's affecting me? Nothing. I go straight up. So, the equation for this, really, very, very simple. How fast am I going? Just do distance divided by time. All right, take the distance. 1 full circle, 2 pi r. Done. Take the time. So capital T here, this is called period. Period is defined as the time for 1 revolution. So distance for 1 revolution divided by time for 1 revolution. Distance divided by time, ta-da, we got velocity. That's tangential velocity. If you're moving at a constant velocity, which is all of these problems I'm giving you all. All the ones I'm giving you all are something uniform circular motion. It is not spinning faster. It is not spinning slower. Constant velocity. It is literally circumference divided by the time it takes to make that path. You all actually did this problem in one of our first problem sets problem, the Earth going around the sun. I said find the velocity of the Earth. You took the entire orbit of the Earth, 2 pi r, and you divided by the time it takes for the Earth to make 1 revolution. I'll point out that problem to you all in case you're like, what is he talking about? So you all actually already did this. You derived this equation if you solved this problem in my problem sets. Look at that foreshadowing. Didn't even realize you were learning. Maybe you did. It was all the way in unit conversions. Look at that. The average distance between Earth and the Sun is this. Ta-da, there's your radius. Calculate the average speed of the Earth in its orbit in meters per second. You were calculating tangential velocity. You did the circumference divided by the time it takes for the Earth to orbit the Sun. Yeah. I did not turn the live back on. Thank you. I appreciate that. All they heard is my beautiful voice. And Leo's. No, thank you. Let's see, what did they miss? Oh, thankfully they just missed this one. Thank you, I appreciate that. Because, yeah, that is a common thing I forget to do. All right, so there you go, 2 pi r over t. So there's 2 pieces here. You need to be able to figure out the direction, and you need to be able to calculate it. So let's practice both. Okay. So something is spinning clockwise. I am purposely not going to draw a bunch here. What is the direction of the tangential velocity at the point shown below? I.e., if I let something go, I spin this in a circle. This is tangential velocity. I spin something in a circle clockwise. I have to do some brain things to figure out which way clockwise is for you all. This is right? It's counterclockwise on my end. It's clockwise on your end. If I release it on the bottom, which way will it go? Remember the case in point, straight line. It needs. None of these options are up and to the left, or like up and then it curves. Up, down, left, right. All straight lines. What's the right answer? There is only one right answer. This thing will go in one direction. It will not go right and then left. That's weird. And I'll teach you all how to draw this on the pictures in case you're not sure.
Right? Like this is the logic that
Yep, that's it. What'd y'all say? That's literally it. Yeah, literally if you can visualize it. All right, we'll go for 15 more seconds because. All right, in 5, 4, 3, 2, 1. All right. So you know what? Let's test it. Yeah. So it's very unfortunate. I meant to bring Demo Duck. If y'all noticed, Demo Duck had a string around his neck. That's why. So I could spin him in circles. But the reality is I left him in my office, so he's very lonely, and he's very sad he didn't get to fulfill his purpose in life. Make certain you find your purpose in life. His is getting thrown around. You know, once you find your purpose, you'll be a happy person. He's very happy, trust me. Come meet him in my office hours. Oh, my office is basically all set up. I got a nice little tea station. I went to Sam's, I got chips. I got fruit snacks. You're never too old for fruit snacks. Okay? You know, an easy example of that. It is surprising that pouches have become like a thing that people that aren't babies eat nowadays. It's wild to me, but it's a thing. Pouches, they've been marketing them for people, which is fine. Like, eat what you want. It's all food. Yeah, it's great. Sorry, this is completely. So my best friend, he also did his PhD here, and he works at some research thing up in Canada, and they like stock snacks, and like one of the snacks that the scientists recommend is the pouches and fruit and like the little fruit boxes or fruit juice boxes, apple juice boxes. So anywho, if it's good enough for PhDs, it's good enough for you, right? But it's just a funny aside. Anywho, that's enough aside. All right, so great. If I swing this thing really, 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 really fast, and then I let it go. Yeah, it scares people, right? I was holding it over here. But I really did want to see how you all would react. So anywho, yeah, if you swing it and then I think I'm doing it the right way, right? Yeah, it's backwards on my end. The really important thing about clockwise and counterclockwise, depending on what side you're on, it's opposite. So that is an important thing to remember. If you're viewing it face on, it's clockwise. If you're viewing it from the other side, it's actually counterclockwise for me. Yeah, if I release it, it goes, well, okay, caught my finger, but you get the idea. It goes to the right. You know, so on and so forth. Yeah, my right, your left. The answer's left. But on a picture, you know, you might not have this apparatus on you. So what do? Oh my gosh, we draw a picture. We do clockwise. And then here's the strat that I use for drawing the tangential vector. So something that if you just draw a little line here, a little straight line, and then you make that line bigger. And you just have to decide which way do I make that line bigger. Do I make it bigger to the left or do I make it bigger to the right? In this case, use that clockwise. And that's literally how you do it. Make a tiny line, make it longer. That's how you make the tangent line to anything. Tiny line, make it longer. So in this case, it's to the left, easy peasy. We move on with our lives. All right. Yeah, that's fine. I didn't mean to actually exit that. I thought I'd have another question, but I didn't. Anyway, all right, but what keeps it in a circle? Whoa, what a good question. It's a string in this case. But in the case of the Earth going around the sun, what's keeping it in a circle there? Gravity. And what does gravity cause? What's gravity cause that we've been talking about all last week with projectile motion? If there's gravity involved, it tells you a certain variable. Oh, look at that. It all connects. If something's going in a circle, its velocity is changing. So this is a very, very important thing to realize about velocity or acceleration. Acceleration is the change of velocity. Velocity is a vector. So here's the really, really, really important thing to keep in mind. Acceleration can make your velocity go up or down, or it can make it change direction. If you are changing direction, you are changing your velocity. If you are changing your direction, you are changing your velocity. Which, again, one of those, if you think about it enough, eventually that'll make sense. But easy example of that. Let me draw my velocity vector. If I'm going this way, let's define this as the x direction. If I'm moving to the right, my velocity is purely, let's just make up a number, 2i hat plus 0j hat. This says I am moving 2 meters per second to the right. I'm not moving forward or backwards at all, or up and down. But what if I do something wild and turn? Oh my gosh, insane, right? It sounds stupid. What's my new velocity vector? It's 0i hat plus, let's just define positive as towards you all. If I turn, that's my final velocity. I was moving 2 in the x direction. Now I'm moving 2 in the y direction. My velocity value, my magnitude of velocity is the same at every single point, but the direction changed, and that means I accelerated. And that's something really, really, really important that as we get into forces, we're going to talk about. A changing direction means you are accelerating. A changing direction means you're accelerating. Acceleration does not always mean velocity goes up or down. I mean, in this case, it actually does mean velocity went up or down. My x component velocity went down, and my y component velocity went up. So numbers did change. Anywho, so we call this in a circle centripetal acceleration. The word centripetal from teaching high school I learned means center seeking. It's a fancy word of saying it points towards the center. The acceleration is towards the center always. And there's a really easy example to prove this to you all, that you all know. It's the Earth traveling around the sun. Which way is gravity pointed? Towards the sun. So yeah, if you're like, why is it towards the center? Just connect it to something that you're familiar with. Here's the sun. Here's Earth. Gravity points towards the sun always. Look at that. That's an easy proof for you all to kind of be like, yep, that's definitely true. In the case of the string is the one pulling it instead of gravity. But gravity is just kind of like a string, an invisible string that pulls things. So there you go, y'all. And the equation is vt squared over r. That t just stands for tangential. That is not time. That is not time. A really common mistake that people make is they write this as vt squared. That is not velocity times time. This vt is tangential velocity. Tangential velocity squared divided by the radius. This equation comes from some geometry that you can kind of do with this. I'm not going to spend the time on it, but it is kind of interesting. It has to do with, you do a tiny little time step and you use that to derive it. To be honest, I'd have to look up the derivation to remind myself. I've looked at it once or twice. It was a while since I've done so I forgot. But it's based on geometry. It's based on geometry. It's not derived. It's observed, not necessarily derived. I guess geometry you could say is derived. Anywho, its acceleration units are meters per second squared. Very, very important. And after we do this, we're done with circular motion. Yeah, that's literally the last thing. And then we're going to get into forces. Yeah. So we'll practice it, as always. Yeah, today's just kind of Tuesdays are often just a lot of information. That's where we cover all the concepts. That's where I introduce the things. Yeah, sorry, I have to always do this. One day I'll figure it out. All right, but very, very, very important. It's always pointed towards the center. Centripetal acceleration is always pointed towards the center. All right. Pachow. All right. Let's see if your brain, if that has made sense in your brain. I could say something a million times, but this is my way of seeing it if it's settled. A ball is being swung counterclockwise. What is the direction of centripetal acceleration at a point located at the bottom of the circle? As always, check with people around you. If you have different answers, one of you is wrong. Or both of you is wrong. Yeah, there's one on the wall. Oh, yeah. All right, let's see y'all. There you go. 10 out of 10. All right. All right. Let's say you all over here. Okay. It's literally that's it. All right, looking good, everyone. I'll close this out in 5 seconds. I think everyone's answered. 5, 4, 3, 2, 1. So one of the fun things is this little thing up here shows me your responses. So what was exciting to me is I saw a bunch of people had the wrong answer, and now as I've walked around the room, people have less people have the wrong answer. So it shows that the benefit of working together. It's amazing how that it helps us identify mistakes. So yeah, it is towards this. It's up, and it's literally a simple. It's called centripetal. It's towards the center. Like that's what the word centripetal means. It's great. It's a really fancy sounding word that just means towards the center. I'm going to mention this other word now, and then you won't really see it. The centrifugal gets mentioned. Centrifugal force. Centrifugal, I guess, acceleration. It is a way of conceptualizing what's happening, but we're not going to use it necessarily in this class outside of me mentioning it like this, and I'm going to make some asides. I will never have you calculate centrifugal anything, though it is a useful way sometimes to think about things. Even though it's not like a real thing, energy is not a real thing as well. We'll get to energy, and that'll be its own fun thing. There's lots of things that aren't real, but they can be still useful, so... Anywho. All right. Wow, this is funky. Oh my gosh. Okay. You may be like, what is going on here? I'm fairly confident last year when I taught this class, my pen died. And so I had to type out all the stuff. And I didn't realize that happened until I looked at this slide now. So look, steps 1, 2, 3, 4 are solved for you, and now they're not. So great. Have fun. But yeah, that's why that was all typed out, was my pen died last year, and so you make do with what you got. So an experimental jet rocket travels around the Earth along its equator just above its surface. At what speed must the jet travel if the magnitude of its acceleration is g? Bunch of things. Classic. Draw a picture.
Oh.
Write down the givens. Write down what you're solving for. If ever you read a problem and you're overwhelmed, just start going through the steps. Because that is literally, if you ask me, like, hey, what do I do? That's literally what I will tell you to do. And you will find once you just start going through those steps, you'll start to reveal how to solve the problem. Just trust me in that if you don't believe me. Just start going through the steps, even if you're like, what's going on here?
You don't see it as a North American
That's a good question. Yes. Let me think about it. Because, so technically the rocket could be speeding up. So in that case, it could have a acceleration in addition to a centrifugal acceleration. Technically, okay, if it's going to maintain a certain good thing, that's one of the really interesting things about orbits. Actually, is how these No, it's very because it's not falling. That's what's special. So what's special about this is this rocket isn't falling to the earth. That's what's special about this. Because you may be like, every object, it's a very valid point. Every object in the air, its acceleration is g. Yes. But this one's not falling. This one is outrunning gravity. It is experiencing the gravitational acceleration. But to kind of draw a picture of this, that's kind of interesting. A really weird thing that you might not realize with orbit, when you launch a rocket, you want to orbit a rocket, you don't launch it straight up. If you launch a rocket straight up, you know what's going to happen? It's going to fall back down. Eventually, gravity's going to pull it back up. This thing, if you launch a rocket straight up, it's not going to start orbiting the Earth. It's just going to go up and down. So anything in orbit, anything that goes around the Earth, is actually going on left or right. And it's literally outrunning gravity. Because it like moves a little bit to the left and then gravity pulls it down. It moves a little bit and then gravity pulls it down. It moves a little, that's kind of an exaggeration picture of it. But literally when you're orbiting the Earth, you are in forever free fall. You are just outrunning the gravity. You are outrunning the Earth. Because when you move a little bit, you move a little bit further from the Earth and the gravity pulls you down, It's a really weird idea, but it's something very important to think about. So when they launch rockets, they launch them at an angle, and everything orbiting the Earth is just outrunning gravity. It moves a little bit tangentially, and gravity pulls it in a bit. It moves it tangentially, and gravity pulls it in a little bit. It's a really crazy idea. Everything orbiting is actually in forever free fall. It's forever falling. It just is escaping. It's moving a little bit. Yeah. Think about it some. But anyway, all that to say, to stay in a circle, it has to be traveling a very specific speed at this specific radius. This is how orbital radiuses are decided. It's based on how fast you're going. If you go faster, you'll achieve a different radius. Look at that. Orbital mechanics, just from simple circular motion. And let me give you all the answers so you can check your work. It's in the problem sets somewhere. I didn't tell you which one, which is bad on me. It turns out you have to go really fast to outrun gravity.
Especially at the Earth's radius.
Yeah, at the Earth's radius too. So this answer is not realistic for being in air, but we're making some concessions here. Yeah. Oh. Yeah. Yep. Yep. Oh, that's classic. Yeah, yeah. No, I'm not gonna show my daughter read you that. They want to do it also. They want all the reason you have to read them, so she can carry around. That's only so. It makes us look best. Like we've also done the bolt. Yeah. That makes no sense.
Oh, this is just the
Yeah,
fine.
you're right, Kevin. Yeah, so we'll take that is a very valid point. So the acceleration here, we're going to put as a positive number. That is important. The acceleration we're going to put as a positive number because direction, when it comes to centripetal acceleration, is let's just take some cases of this. Let's say this thing's going clockwise. The acceleration here points inwards. It points here inwards. It points here inwards. It points here inward. Positive and negative when it comes to this acceleration doesn't really mean too much. Except all these equations didn't actually have vector symbols over them for that reason. It is always towards the center, but do you say that's positive? Do you say that's negative? So in this case, any number you put in, you put it as a positive number. You decide the direction from the picture. You decide the direction from the picture.
Yeah, this whole time we use this equation all the time.
Am I showing class? That's just the right.
Yep. Yeah. Did you just make that?
Yeah, I just made it.
No, so that's the really cool thing about when you're a learning assistant, when you're teaching other people things, you're gonna make tons of those connections that it's stuff you've been using the entire time.
Yeah.
But then when you have to use it, you have to think about it on an additional level.
Yeah, because it's just orbital velocity given
Yeah, it's great. I thought you had a question. Alright.
That's what mine right now.
Yeah, because there's so much with this one velocity given, and then you just replace the acceleration with gravitational constant mass. Yeah.
It's not
Simply you're showing
So all other problems, what is negative
I can't believe I never made that connection before, now. Going all the way back to physics 1.
Yeah, so it is accelerating. The thing is, gravity is affecting, so technically on a rocket it has in space. So thing on Earth you have waves that push off the Earth. In space, you don't have that. So they don't have rocket boosters literally pushing them away from the Earth. So instead, literally what they do is when something's orbiting the Earth, if it's moving to the left, it literally when it moves this way, this is a farther distance. So by moving this way, you actually move farther from the Earth, but then gravity pulls you down. And you move a little bit further, and then you kind of, that's a circle. Which is the crazy, so that's things going in space, they're actually pushing, they're really just outrunning the Earth at the same rate that they fall Why? So yeah, they're always accelerating towards a certain acceleration, or what that acceleration is. Yeah. Sure, and that's only for so this probably be more clear at what speed the travel versus if it's magnitude acceleration g and it's making it perfectly circular, that would change it. That would also change it for it to stay in a perfectly circular pattern. Otherwise it would fall or make it elliptical. Alright, so just to kind of quickly work through this, I think most of y'all got it, but in case you didn't, what's cool here is there's literally only a single number. I guess I gave you two numbers. So I gave you radius in that scientific notation, so 6.37 times 10 to the 6 meters. That is roughly the radius of the Earth. In case you haven't seen this number written out before, it's kind of interesting. 1, 2, 3, 4, 5, 6. So this is the radius of the Earth. 6 million. Oh, did I? Yeah. 6,370,000 meters. That is the distance from you to the center of the Earth, roughly. It's just kind of interesting to see that number. That's a big number, obviously. It might not be as big as you think or things like that, but wait, is that the radius theory? Yeah, that is the radius theory. Right?
Well, yeah.
Okay, good. I'm double check. The reason I'm double checking, there's sometimes where I'll be mean and I'll give you a problem where I say it's this far above Earth's surface. And in that case, you have to add that to the radius of the Earth.
Yeah.
So that's why I had to double check myself here. But I wasn't mean in this case. I just gave you all the number. And you all got the answer, so I think I would have got more questions. Anywho, centripetal acceleration. We put a little c next to it. It's good to be clear in your variables. If you just put a, that's fine. But spoiler alert, at some point we're going to have tangential acceleration. Yay. At some point. So it's always good to label your variables. All right, step 2, what are we solving for? We're solving for velocity. So step 3, what equation has these? AC equals VT squared divided by R. And step 4, it's just plug and chug. VT equals the square root of AC times R. Ta-da! Very straightforward, very simple, classic given missings do. Okay. So now we're going to move into forces. So we'll get started a bit on that. And then go from there. So this is an open question that I want you all to talk about with your groups. How do you Great, acceleration is a thing. How do you make it happen? Figure out with your groups. Come up with some scenarios. There is an infinite number of answers to this. Infinite number of answers. Don't worry, I saved you. What is it for? Give me some specifics. Kinetic gravity's one. How would you add it? How would you apply it? These are all like physics words, like literally anything that's dry spot. Basically, this idea of what it's like. Because sometimes we use words so much literally every single word that. What's the force?
I think
Pick a real world example. What do you know? All right, y'all. So what y'all got for me? What are some ways that you cause an object to accelerate? To change its velocity / change direction. All right, put something that, put a rocket on it. Sure, what else? What if y'all wanted an object in your desk to accelerate? What would you do to it? If I want this ball to accelerate, what am I going to do?
Spin it.
Yeah, you could chuck it. Great, I accelerated it. It wasn't moving. Now it is. Now it's not. Why did it stop moving? Hit a wall. All right. What are some other buzz? No one said the buzzword yet. Force. Force. What is a force? What is a force? How do you know if something's a force? Yeah, I think math. Then we'll get to the equation. F equals ma. But what is a force? If you had to explain it to an elementary school student, how would you describe it to an elementary school student so they could understand it? A push or a pull? That's kind of the fun, and we're going to enter into some circular logic here. You can't. So the better question. So forces, you can't actually. Here's a weird. You can't measure a force directly. That may sound like really silly. Be like, of course I can. I can measure. There's plenty of like scales and things like that. Anything that measures force is not actually measuring force. It's measuring acceleration. And technically it's not actually measuring acceleration. It's measuring the change of position with respect to time. Or it might be measuring like a spring or something like that. Or anyway, it is really interesting to think about any device that you all use. What can you actually measure? A lot more things that you use calculate things. A lot of measurement tools you use measure something and then they calculate something else, and that's what they actually show you. That's a really interesting thing to kind of realize. Or they use some analog system that converts, so like your car has an analog system that converts how many rotations of a tire to the speedometer. It's not like measuring how fast your car is moving. It's measuring how many times your wheel spins, and then it knows the radius of your wheel, and it assumes no slipping, and based on that it knows the circumference traveled in one rotation, and yada yada yada. Anyway, so all that to say, it's important to think about, there's a lot of words we're going to use in this class. Force, energy. Don't fall into the trap of just their word. Don't fall into the trap of just using them willy-nilly and like knowing the math. If you can't explain it to an elementary school student, then like how much, and this may sound silly, that is kind of a metric of how well do you know it. Can you explain it to someone who has never heard anything about it before? That's a great strategy for making certain you understand something really well. Teaching something to someone is the best way to learn it, as weird as that sounds. It really tests if you actually understand it in detail. So anyway, think about that. Anytime I say the word force, how would you describe that to an elementary school student? When I talk about the word energy, energy is incredibly hard to explain. Like, you'll see, when we get to energy, you're literally going to hear me say it's made up, because it is. We'll get there. All right, so forces that cause things to accelerate. That's kind of, in my opinion, the best way to define it, which is backwards what I just had you do. But we have to start with what you can measure and then make up things. Force is not something that anyone observed. Newton wasn't out there like, oh, that's 5 newtons. Like, he had to invent forces. There was plenty of people that were measuring distance, because you can see a distance. Someone's like, that rock is this big, and this tree is 5 rocks tall. Like, distance is fairly straightforward. Time, that's a crazy thing. That's its own challenge. But force, developing force is not as trivial as it sounds. Newton was an absolute genius, and you're going to realize that he came up with forces. He discovered a lot of things with light, the refraction of light. What are some of the other things, Leo? And what other things did Newton do? He did light, he did forces, he invented calculus. Huh? He did telescopes. I think there's probably a couple more things. He's one of those people I guess you call like a Renaissance man, someone that's like an expert in a bunch of different fields. Insane. He literally came up with the equation for universal gravity between the Earth and the Moon, and the Earth, literally 2 planetary bodies, which we're going to see that equation eventually, the equation for literally any 2 bodies. He's the one that discovered everything with mass affects each other. Wild. Like, we hadn't been to the moon at that point. Like, that's obvious. But he measured the force that the Earth pulled the moon with. Like, and you have to even think about how you would do that. And that's how crazy this is. This guy did this 200, 300 years ago. He measured literally the exact, like, pretty accurately the force that the Earth pulls the moon with. Wild. Absolutely wild. It's really important to respect what people have done in the past, because something that's kind of, people in the past were not dumber than us. They just didn't know as much as we did now. So what you all are building on now is what everyone before you has discovered. And so any progress we make isn't from zero. It's from everyone after us. There's the classic saying, I think it might have been from Newton or someone, I can only see this far because I'm standing on the shoulder of giants. Everyone passed, was it him? Yeah, it's a great saying that literally every discovery we have now is built upon previous discoveries, and you all just happen to live many 10, 12,000 years after humans started farming. Like, it took time, y'all. And it wasn't something that it wasn't written on a wall somewhere and someone found it and said, that's it. We had to discover these things, and you all have brains and you can discover new things. It's great. All right, push or pull. All right, this next slide is kind of, I'll do this, and then I'll do this one, and then we'll kind of pause and then get into Newton's laws. This is a very this is a very interesting slide that you will never hear me talk about 3/4 of it. And half of this you'll never hear probably anyone talk about ever again. There is 4 fundamental forces in the universe. It's a really interesting concept as far as we currently understand. Every single push or pull in the universe goes into one of these 4 things, and they do not interact with they're separate from each other. Gravity is completely separate from the electromagnetic force, is completely separate from the strong force, is completely separate from the weak force. They're all independent of each other. Literally every single push or pull in the universe falls into one of these 4 things, or some combination. Yeah, so there is the grand unified theory is this like dream of physicists that there's something that will combine all these together and explain them. But we don't know. Yeah, anyway, gravitational force we'll learn about in this class, very straightforward. You all have experienced it. It explains why things with mass attract each other. Funny enough, this force explains literally only one thing that you experience in life. The fact that you're stuck to the floor. That is literally the only thing that's explained, and the Earth going. But as far as for you personally right now, the only thing this tells you is that this is the reason why you're stuck to the floor. Or chair, whatever you're stuck to. That's it. Every other push or pull, the vast majority of them are actually the second one. The electromagnetic force explains the vast majority of the forces that you experience. When you push something, you'll learn this in physics too. Nothing is actually touching. The classic, once kids learn that, I'm not actually touching you, it's just stupid. They hate it. They know they're being punks. But it's the electrons. When the electrons get really, really close, they repel each other. So literally any contact you make with anything, it's the electric fields repelling each other. You'll learn that in physics too. The strong force, this is where my assistants might be able to help me. Like, I will tell you all what I know, and they can add on what they know. And if they know a bit more, that'll be great. But it's literally like, I know like 2 sentences for the next one. The strong force, all right, so you are going to learn in physics too that protons repel each other. Positive charges, opposites attract. Like charges repel. But the nucleus has a bunch of protons together. Those are positive charges, but they're stuck together. That's weird. So there's something called the strong force, and I'm going to give you all a bunch of mumbo jumbo. This is what I learned in my undergraduate quantum mechanics class, and this is literally the extent I know. Protons are made of quarks. And the quarks exchange gluons, and this holds them together. That's it. Does that make any sense? Not to me, but it's words. Do you all know any more about the strong force than quarks and gluons?
The force can only act at very, very small distances, so even like a slight disturbance, if like one proton decides to go a little bit far away, it's going to stop working.
There we go. That's another new thing. So it only works at very small distances. If they move a little bit further away, the electromagnetic force takes over. So I didn't realize that makes sense, right? They're really close together. All right, weak force. I know even less about this. This explains radioactive decay. That's all I know. Why does uranium break down into other things? Because of this weak force. Do y'all, Leo? Yeah. Do you know any more about that? Nope. See, look at that. I've done a lot of physics. They've done a lot of physics. Unless you're going into like nuclear engineering or a nuclear physicist, you probably won't learn about these that much. Maybe chemists will. Maybe. I don't know. Ask a chemist. All right. So last thing I'll tell you all, there's different forces. There's one that's literally contact forces. Things are physically touching. The reality is, on a fundamental level, those are field forces. But for the sake of convenience, we'll treat this. Again, this is just vocab. I'm not going to test you on these words. And with that, that's kind of a good pausing point. So we'll take a break till like 9:23. Give you all, something like that. This is a great opportunity to, one, take a break, or two, if you have any questions for me, LAs, anyone. You can also ask us things during this time. And we'll get into Newton's laws after this, and then we'll see how far we can get today. The farther we get today, the less we have to do Thursday. What's up?
You're saying that force is measuring acceleration, but it's not really acceleration, it was position in respect
Yeah.
to time. Isn't position in respect to time just velocity?
Yeah, but you can't measure, so even velocity, you can't measure velocity.
Yeah.
You can only measure where something is. So like, because think about how would you measure velocity? Let me ask you that question. If you had to measure how fast something's going, how would you do it?
Well, you said it's basically distance over time.
So you'd have to measure the distance, and you'd have to measure the time. So basically, a lot of measurements actually do just boil down to measuring location and time. Radar guns basically do that, but radar guns, funny enough, I guess they work well firstly. They shoot a laser at something, and they know when they shot the laser, and then the laser hits something, and then it bounces back. They know how fast the laser is going because it's light, and then they can measure the time it takes, and then they can use that to calculate position, and then use that to calculate velocity, which is kind of funky. But yeah, it's an interesting question.
Yeah, it's like, it makes sound like the way you were describing that acceleration and velocity were the same thing. Because
Oh, no, yeah.
force is acceleration, which is position to time. So it's not like
Oh, yeah. You measure it with, so you'll measure acceleration by doing positions, which you'll then use to calculate velocities, which then you'll use to calculate, or you can just skip straight to acceleration. Yeah. That was the idea I was mentioning. So that if you want to measure acceleration, you basically have to measure position, and then you go from there. Yeah, that's a good question.
Yeah.
Oh, and I just want to drop anything in China. Please feel free.
I know a lot about gravity. Well, not a lot, but like that's where I know the most.
Yeah.
I don't know that much.
No, we'll do universal gravity.
Yeah, that's like my favorite.
Yeah, that's also my favorite. I love.
Yeah, I need to include a escape velocity problem. I don't currently have one, but it's such a simple problem. You have to know universal gravity, and you have to know what to do with it.
Yeah, there's my favorite part of physics too so far has been the electric force because it's just gravity. So I can solve that.
It's at least the same. It looks the same, and that's one of those weird coincidences that makes people think there's a grand unifying theory, but yeah.
It's kind of just inversely proportional to the square.
Yeah, it's wild. It's weird.
It reminds me of that meme where it's like I've connected the dots. It's like you connected shit.
No, it's good. It's fun stuff to think about and talk about. So, what's up? Yeah. Oh yeah. Yeah. For sure. It's a good problem. It's a class. It's the only problem. And they have a good they show that you can redirect, fully just redirect, or and then you have to do some like creative thinking about what that means. If you've done it before, it'll be easy. So, the nice thing is if you have taken it in the past, there's stuff that still makes sense. Yeah. 3 years. Did you pass these? Yeah, I passed all of them. Oh, is it the algebra based? Yeah. 260. It's all you basically got. Which is another at most So that's fine. That makes sense. You know, why not? Because you could, I guess, that was more well, I passed. I did it. And I was like, oh, so my physics major. Yeah, my physics major. They called me, well, maybe I can wear, like, just in case, you know, whatever, you'll have a really strong foundation. You'll have a really strong foundation. A strong foundation in physics does go a long way.
Nah, bro. It's about to shoot you. Nah, bro.
Water, syrup, salt. Yeah, and I didn't take anything. That's true. Like, you know how we're X, Y, Z. It's just the same thing you do in top two. It's mostly like, it's literally like it's the whole process. You get to like nose control, stuff like that, partial Yeah, what's up?
My Wi-Fi.
No idea why that is. Because it's fairly like and like common. Yeah, I never took any class. I I have no idea why, but it's just like a real thing. At least at this school, I never learned anything about the my entire life.
Well, some people like.
A lot of people fail that. Yeah,
I would probably go through physics 1, 2, 3, then learn how to do physics. So literally at any point you're like, oh no, I feel pretty good about 4 steps problems. At that point you can learn anything. At that point all physics boils down to, yeah, it's observation of reality, and there's new variables that you can identify, and then you solve it, and there's equations that relate to them. All physics is basically just this equation that relates to other equations, or variables that relate to other equations. Alright, so we are probably going to get through this entire PowerPoint base today, which is like, woohoo, awesome. What that will mean is we will then start, and you'll be like, well, that means we're like super ahead. The reason for that is this PowerPoint is it's all concepts. It's all concepts. So we're going to start rolling. Next week is kind of like, 1D kinematics took us like a week and a half because there's a bunch of equations and practice problems. Applying forces is going to take us more than next week. So that's what we're going to start on Thursday. And so we'll have a week and a half to actually do forces. So that's sometimes how this stuff kind of goes, where 1 week will be a little bit shorter, the next week a little bit longer, or vice versa. Anywho, to that end, we'll get through this, kind of see time-wise, see what's reasonable, see how many things I'm trying to shove into your brain if it makes sense to do more. But there he is. Newton, Isaac Newton, the mad lad himself. That's what he looked like. You can decide hot or not. It's always one of my favorite questions with him. Beauty is subjective. He makes a striking figure. I mean, it's a painting, so it's going to be a little striking. But, fun fact, he was, I think he might have been in a relationship, but he was actually, I think, single his entire life, and there's some interesting stuff you can look into about that. Married to physics, or who knows what. But, absolute genius. There is people that come by, you'll meet people like this, I meet people like this, where you interact with them and you're just like, how does your brain work that way? Not like in an insulting way, but like in a, how are you able to do the things you're able to do, because it's extremely impressive. How are you able to make these connections and develop these things? Look, there is people, so many people, whenever I talk to any theoretical physicist, I sometimes feel that way. And there's also, I had a few high schoolers I interacted with. There was one high schooler who, he literally, I think, he missed one question on the PSAT. Which is just and the year before that he got a perfect score on the PSAT. Just how does someone's brain, how? I was nowhere close to that. You will meet people like that. There is varying levels of these people. And again, everyone's got different giftings and talents. Doing really well at physics is one talent. Being really good at socializing with people is a talent. Being able to connect with people emotionally is a talent. Many giftings, and you're going to meet people that are really gifted in these areas. And when you do, just kind of appreciate that. It's really interesting. It's the beauty of mankind. But this guy, he made connections that no one else did. The man invented calculus. He discovered the universal law. I already gave you some examples. Just wild. Even coming up with the idea of force, it's going to may or may not sound obvious as we talk through it. He came up with these laws. Laws are fundamental observations of reality. They're just based on fundamental observations of reality, and it may seem trivial, but it's not if you're the first person to come. It's because someone else already came up with it for you. It's like the wheel. Of course the wheel is great. Well, yeah, you grew up with wheels. Back when someone invented the wheel, it was a big deal. All right, so to that end, we're going to get through the 3 laws. Each one of them there is so many consequences of each one that some parts you'll be like, duh, and other parts are going to be like, ooh, that doesn't sit right, and it might have to take a little bit for you to accept that it's accurate to reality. We'll see. All right, so if you fire a bullet in space, what will eventually happen to the bullet? In space, away from Earth. This is not saying on Earth I fire a bullet into space. No. I am in space. I am floating in the void. and I shoot a bullet. I shoot a gun with some bullet in it. What's going to happen to that bullet? Classic physics. All these are going to be classic questions I'm about to hit you with. If you're taking physics before, you're going to have heard these questions before. How would you describe its velocity? What's All right, I'm gonna give you all like 7 more seconds because there's no math here. Go with your gut. We'll close this out in 5, 4, 3, 2, 1. All right. Great job, everyone. You all got the right answer. And I walked around. Why? Who feels confident? Why? Yeah.
An object stays in motion unless an external force.
So there's Isaac Newton. Yeah, his law: an object in motion stays in motion until a force acts upon it. So that is the formal definition. But if you had to, so why is that the case in this specific example? Why does this bullet? Let's look at this specific example. What details about this means it won't speed up or slow down? There's no gravity. Is there anything pushing it forward after it leaves the gun? No. There's nothing pushing it forward. There's nothing pushing it backwards. That's really what this boils down to. Why is this so So Isaac Newton discovered this relationship. There's the right answer. Y'all did a fantastic job. He's the one that came up with this. So this is the formal kind of wording. A body at rest remains at rest, or if in motion, remains in motion at a constant velocity, unless acted on by a net external force. It's a bunch of words that say that things keep doing what they're doing. Everything on my desk up here will be on my desk unless someone moves it. It's magical to kids. They close their eyes and you move away and they think you disappeared. No, you just moved. You had a force acting upon you. It's something you've experienced all the time. But here's the thing that's wild. Isaac Newton didn't know about space. He couldn't actually test. So air resistance, he had to conceive of the idea that, there's this thing called air and it slows it down. And if there wasn't air, things would keep going forever. That's a wild idea because you all have probably never seen something get tossed and go forever and ever and ever and ever and ever. You've seen videos of stuff in space, and that's the example I gave you. We hadn't sent anything to space 300 years ago. That's a very recent development. This is not something you could test, per se. So he had to come up with this idea that if air resistance didn't affect things, if gravity didn't affect things, they would go forever and ever and ever and ever. That's like a big jump to be able to do that without actually testing it. Crazy that someone came up with this before all that. I put my less formal definition. This is how I'd explain it to an elementary school kid. Things keep doing what they're doing until someone, I would probably change it. They keep doing what they're doing until someone pushes or pulls it. Until something pushes or pulls it. Inertia, we're going to reference, especially when we get to momentum. It refers to the property of an object to keep doing what it's doing. Something with a large inertia, it's like a big truck. Something with a small inertia is like an apple. Easier to stop, harder. It depends on how fast they're going, depends on how much mass they have. Yeah, so fairly straightforward. It's what you expect, but it's really impressive that he came up with this when you kind of think through all what he had access to at that time, and the fact that he realized that this thing's do that. I will never test you all on, and I'm gonna fact check I'm not gonna ask you all to list this definition kind of thing. I'm not gonna ask you all to say which of Newton's laws explains this situation. I will not do stuff like that, but I will ask you questions like I just did. So just so you all know, I'm never gonna ask you list this which of these is Newton's first law? Or out of these, which law is it? Because I don't need you to memorize exact wording, but I need you to know the concepts. So that's what I'll test you on, is the concepts. So all these clicker questions I give you, those are kind of examples of what I could ask on a test. All right, so yeah, if an object is slowing down, a force is acting on it. That is a way we can measure forces. Something's slowing down. Something must be affecting it. You can discover what that is. If something is going at a constant speed, then the net force is 0. So this is one of those, if you're in a car going 60 miles per hour, yes, you are having to hit the gas to keep the car going forward, but the amount that your car is getting pushed forward, air resistance is pushing it back the exact same amount. So that's kind of one of those things that, yes, you have to keep hitting the gas, but the net force is actually 0 because air resistance is canceling it out. And yeah, if there's no forces, things keep doing what they're doing. That's statics in a nutshell. Statics in a nutshell set all the forces equal to 0. Solve things. For those that take that class. All right. Oh yeah, and the interesting consequence. So this gets mentioned in some video games. I remember there's some line. I think it's like in Mass Effect or something. I don't know. Where they're like, in space, if you shoot a rocket or you launch something at another ship as a projectile, you better make certain you're going to hit it. Otherwise, I mean, that thing will travel forever. If you miss, anything in space will keep traveling forever. There's a really interesting consequence of this. So satellites, they're in space. They keep going around. There's technically some small amount of air. The atmosphere, there's no like set point where the atmosphere ends. It just gets thinner and thinner and thinner and thinner. So things do have a slight amount of drag even when they're in space around Earth. But yeah, if a satellite breaks into a million pieces, all those millions of pieces, there's this whole effect. It's called, what's the name of it?
I don't know the name of it. It's like a compounding space junk issue that we have. That one thing breaks into a billion pieces, and then that will hit something else. It'll break into a billion pieces. It's like this cascading effect. That's a really big problem in orbit.
It's got a name, something syndrome. Does anyone know it?
Try and look it up.
No. All right, we'll figure out the name of it. But yeah, if a satellite blows up into a million pieces, those satellites travel really fast, like insanely fast. So if you have just like a single bolt that comes off of a, what was it?
Kessler syndrome.
Kessler syndrome. So this is one of the concerns with putting too many things in space. If a satellite breaks, it'll make a bunch of parts that will then potentially hit another satellite, which will break into a bajillion pieces, which will then break into a bajillion pieces, then break into a bajillion pieces. And if you just have a single like screw flying through space at 1,000 miles per hour, anything that hits is going to get obliterated. Anywho, it's an interesting consequence of Newton's first law. If it's just because a satellite gets hit with something, all those pieces don't just stop and fall to Earth. They'll keep traveling after they've gotten hit. Anyway, good stuff. All right, next one. What's hard to move on Earth, a small truck or a big car? Oh, small car, big truck. The next one is going to be in space. Classic questions. Things that you expect, and then I'm going to hit you with things you don't. All right, what say y'all? Yeah. What aspect of this thing why does it?
I mean, technically,
It literally has more stuff. Count the protons, the neutrons, I don't know. Are they heavy? Okay. I was like, I don't know too much about it, other than it's a but it's got to have redeeming qualities as well. Like Tesla does make some decent stuff. All right, we're gonna close this out in 3 seconds. It's fairly straightforward. In 3, 2, 1. So this is not a trick question. The truck is harder to move. And we're going to get to this. We're going to get to why. But what is fundamentally different about a truck versus a car? Their mass. What is mass? Let's get into that. What is mass? Again, it's a buzzword. You've heard the word mass. What is it? If you had to describe it to an elementary schooler, what would you tell them? Yeah. That's literally kind of the word. How much stuff it has. It literally has more stuff. Now, if you want to get specific and like what's the stuff, it literally has more protons and neutrons. If you counted all the protons and neutrons, it's got more of them. That is our fundamental definition of stuff, is protons and neutrons. So anywho, it's got more stuff. All right, so the classic. What's harder to speed up in space? A small rocket or a big rocket? Small rocket, big rocket, are the same. So basically, the same problem, but you're in space now. What do y'all think? What was the on Earth? What was the reason he said the small car? What was the reason? That's the question, I guess. Is it mass or is it weight? That's not the how much stuff it is, or how much it weighs? To clarify here, when I say small rocket and big rocket, I mean like the big vessel. Not literally, they have the same engine on them, let's say. Same engine. It's literally just one's small, one's big, like size-wise. Replace this, what's harder to speed up in space? A small car or a big truck? Alright, so you're okay, six? Alright. Okay, so in your case, the weight that matters. What do y'all think?
I don't know.
Actually, I'm scared of the ocean.
Alright, I'm gonna give you all 5 more seconds. And we'll close this out in 5, 4, 3, 2, and 1. And here's the cool thing about this problem. It's the same problem, but I just put it in space. And look at the different answers we get. And this is where some people aren't going to like this. The answer is the same logic as the last one. And you may be like, well, what? And this is good. This is good. This is why this is such a crazy discovery. It's not about gravity. It's about how much stuff you're trying to move. It's not about gravity. It has nothing to do with gravity. It could be a million, like, gravity is not actually what affects how hard, okay, granted, friction is a thing. Friction is a thing. But let's take an example of, a big plane. Let's take something that you all have experienced. Think of those giant planes. Think of a big plane in the sky versus a small plane in the sky. They're not touching the ground. And yet, if you put a tiny little propeller on a big plane, it's not going to get it all, like, not much is going to happen. Not much is going to happen, and the same thing applies to rockets. When you're in space, if you had the Statue of Liberty in space, just take something ridiculous large, it's just floating in space, and you tried to push it, you wouldn't really be able to move it much, because it's so much mass. It's about how much mass you're moving, not weight, but mass. Literally, it's hard to move a bunch of particles. So we think of our first law: things at rest stay at rest until a force acts upon it. The more stuff you have, the harder it is to move it, because it's literally you have to move more things. It's a really Newton hadn't been to space. Like nothing had been to space, and Newton figured out it had nothing to do with gravity. Newton figured out that it all has to do with mass, and that's F equals ma. Nowhere. So the force required to move something depends upon if you want to accelerate something. F equals ma. If mass is bigger, you need more force to get a bigger acceleration. To get the same acceleration. Yeah, just rearrange it. A equals F over m. If m is bigger, you need a bigger force to get the same a. Just make up numbers, you know. If I want an acceleration of 1 and my mass is 1,000 kilograms, really straightforward math, I need 1,000 newtons. It's wild, y'all. This is one of those things that, like, again, it seems so, F equals ma. What a simple equation. But to conceive that it's not about gravity, it's about mass, when nothing had ever been in space before and he couldn't actually test this himself. I mean, you could do a frictionless surface like ice or things like that. Yeah, pushing a really heavy box on ice, a really big box on ice, friction's really low. It's really hard to move. The friction is basically 0. So wild stuff. Yeah, so if your mass is 100 kilograms, you know, you only need 100 newtons to push it. Oh yeah, and the unit for force is newtons. Shocking, right? Named after the guy that discovered it. That's going to be a really common trend. Anytime someone discovers or comes up with a unit, comes up with a measurement, it gets named after them. The unit does. Newtons for Newton. When we get to energy, it'll be joules. When we get to current, it'll be amperes. Resistance is ohms. Voltage is named after a guy whose last name was Voltaire. Was it Voltaire?
I don't know.
It's Volt something. Voltaire? Yeah. So when you discover a unit, when you discover a measurement, the unit gets named after you. Anywho, so again, it's so cool. It's so simple, but so fundamental, and it applies to literally every single object ever. More mass, the harder it is to move. The harder it is to accelerate. That's a really important thing. The harder it is to change its speed. If it's already traveling really fast, it's really hard to stop. If it's not moving, it's really hard to get it moving. So, cool stuff. Really, really simple rules with really profound consequences in reality. And not what people expected either, which is great. These are the really impactful questions. These are the ones that make you look at reality different than the average person. That's why these classes exist. Most people could describe a force to you, but a lot of people wouldn't realize it's mass, not weight. It's cool. All right. Moving onwards into the last law, which will also challenge. Again, the first law was honestly the one that was the most straightforward. The second one's going to challenge our views on some things, and the third one is also going to challenge our views on some things. Even though they're such simple statements. Oh, okay. You know what? Sure, I'm going to have you all do this. So this is just kind of testing that equation, see if you all can figure this out. So this is something you're going to see me doing moving forward. I haven't done it kind of up to this point, but one of my favorite questions is, if I double this, how does this other variable get affected? If I triple this, how does this other variable get affected? Being able to determine if I change something, how does the end result change without actually using numbers? That's a really useful thing. If you all, in your engineering stuff, if I use twice as much steel, how much more force can my thing withstand? If you're designing a circuit, if I have twice as many resistors, how much does the computational power increase? Like, these are really important things to be able to kind of do on the fly. So we're going to practice it. You're going to see us do it in the class, and we will use the equations, and I'll walk you through how to do these problems. So object A has half the mass of object B. Yeah, that's going to make your brain have to work. I want to accelerate object A 4 times as much as object B. How does the force on A compare to B? I'm going to even be so kind and draw a nice picture of this. Object A has half the mass of object B. I want object A to have an acceleration we'll draw arrows. That's 4 times bigger. Let's call this A2. So A1 is going to be 4 times A2. This is mass 1. This is mass 2. I'm going to even be kind. Mass 1 is half of mass 2. This is kind of the things you want to be jotting down when you're kind of doing these problems. What is the relationship between the variables? And see if y'all can then figure it out. Oh, is the answer not up there? That's so frustrating if I did that. No, it's fine. No, it's fine. It's good. It's good. I'm good. I was really worried it was like.
I just want to bend my logic.
Yeah. No, that's why I was like, I was really worried it'd be 8. None of the answers are 8. That's good. The answer is not 8. The answer is not 8 or 1/8. Now this is gonna. Also, pro tip to you: you're gonna use F equals ma. What do y'all think? Okay. Sure. Okay, that's a great. Both ways are valid, and that's the thing. When you understand the concept, you help check like. I read interesting that it wasn't harder. As weird as that sounds, it's very common that people do math. It's less common for people not understanding. Yeah, because math is very complex. Yeah. Oh, it's great. I'm all for that. That's what got me into my programs. And then when I started, it made me have to like probably be like so voltage. I didn't actually understand what voltage was until I taught it in my juniors. After I'd taken the Which course do you want to be thinking? Do you agree that A is bigger? You can make up a number if you want. This is one that. It's one of those things like it's a class. Like this is and like and how you write it. Make up a number. Make up B2 or make up because you both agree that it should be bigger. Oh yeah. Alright. Let's say why? You also say me. Okay, yeah, go for it. Yeah. Cool. Okay. So why did you do the half times? Okay. 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 Uh-huh. Yeah. No, that's not. Yeah, that's good. That's good. That's actually, yeah. So you wrote it algebra. So that's actually how I'm showing. Yeah, and so the question will be multiplying, dividing. That'll be what's challenged. We're good? Alright, so I'm gonna give you all a little bit more time on this and then we'll so I'll give you all like 5 more seconds on this. It's interesting, the math here is not hard, it's just setting it up right. So we'll close this out in 5, 4, 3, 2, 1, and we'll close it out. Okay, so I'm going to show you all a couple ways to do this. It looks like everyone did great. Like, vast majority of people, awesome. If you didn't, that's fine. These are going to be classics. These problems are going to be classics. So I'm going to explain it through conceptually first. And then I'm going to write out the math, because the math will then kind of test your logic. So really interestingly in this class, there's the math, and then there's the concept. The math is writing out stuff. The concept is what's going on, and could I explain it to someone? What may seem really weird, I don't know if y'all will agree with me on this, but just trust me that this is the case. The math is easier than the concept. That is something that you might not believe or not, but trust me, you're going to find it out as time goes on. More people generally understand the math because math is very formulaic, very this and this and this. The concepts, each individual idea has its own unique concept that you kind of have to wrap your brain around. But if you can generally do the math without the concept, but if you understand the concept, it'll help you do the math. The concept will help you check your math, help you check whether it makes sense. And the concept, those are the people that make big bucks because those are the people that actually understand what they're doing and why they're doing it. And then you can explain and be able to explain that to other people that have no idea what the math means. I could spit a bunch of equations on here and it would just look like another language to other people. Like being able to communicate something, that's where you make the big bucks. Anyway, so to that end, let's look at this thing. If it has half the mass, it's easier to move. That's kind of conceptually. Half the mass we talked about means it's easier to accelerate. If I want to accelerate it 4 times as much, I need to put 4 times, not 4 times force. I need to put more force into it. So it's easier, it's twice as easy to push, but I want it to be 4 times as much. So then they kind of 4 divided by 2 and you get the answer. So that's kind of the conceptual idea. It's twice as easy, but I need 4 times as much, 4 divided by 2, boom. But let me show you all how to do this a bit more formulaically, mathematically, to prove that. So here's what I do. I have the force of 1 equals M1, A1. You know, let's call them A, because they're object A and object B. So object A, the force of, boom, there it is. FA equals MA, MAAA, which is just sounds like nonsense. FB equals MB, AB. Okay, great. We plug all that in. All right, now, how is this helpful? What's the point of this? All right, we want to find how does the force on object A compare to the force on object B. So we're going to take this equation, FA, and we're going to put in, instead of MA, we're going to use the relationships I wrote here. We're going to put these relationships right here and literally just plug them straight into the equation. So I'm putting the A's next to them so it matches the notation I used here. We're going to write all these variables, AA in terms of AB, MA in terms of MB. Boom, so to that end, MA is 1/2 MB. Great, that's my first substitution made. AA is 4AB. All I did is swap them in. Why did I do this? You pull out all the numbers, you pull out the half, you pull out the 4, and you're left with MB AB. Well, you know what MA, you know what that is? That is FB. Ta-da. So this is how you do it. You write the equation in terms of the thing you want, and then you just make a bunch of substitutions in terms of the other variables. Pull all the numbers to the front, boom, you're done. We are going to practice this a lot in this class because it's very useful to know if this variable doubles, halves, triples, what's going to actually happen to a different variable. That's really, really, really useful to be able to kind of do that manipulation without numbers. And again, you can think about if you're working for a company, why they would want to know this. If I change this thing, if you build this thing with half as much steel, can it still hold the structure? If you build this thing with twice as much RAM, will it be able to do the computation I need it to? Like, these are the kind of thought process. If this changes, how does it affect something else? All right, great. To that end, we're into the last Newton's laws, and then this will kind of be, we'll do this and then talk about free body diagrams, and that'll be kind of the end. It looks like we have a bunch, but it's not that much. All right. Are there forces acting on you in your seat? Yes, no, maybe. I'll give you all 30 seconds for this. Just, throw out your guess. Are there forces acting on you right now? That's awesome. Yeah, you can do ratio. You can do ratio as well. I like doing this way because it's really straightforward. You can do separate ratios. So the right one's on top, and the right one's on bottom. If it works, it works, and we're gonna get lucky, so you'll be able to catch this. That's not a problem. Sure, and that's what we effectively did. I made a relationship between that's totally valid. Yeah, I made B my standard, and I put everything in terms of B. And yeah. All right, close this out in 3, 2, 1. All right, this is not a trick question. We all did great. Yeah, there's forces. Y'all tell me, what are they? Gravity's one. And the normal force. Normal force is a really fancy word that we haven't used yet, though. Let's put it in more, that's even fancier. Electromagnetic is even fancier. Technical. What is literally, so gravity's pulling you down. Why aren't you falling? Chair is pushing you. Fantastic. So the normal force we're going to learn is just the surface that pushes you. Yay, there is forces. Fantastic, fantastic. Do we want to do this one? I want to stay on the train of Newton's laws. We might come back to this. All right, Newton's third law. So we'll come back to that problem kind of at the end and solve it. A 2,000 kilogram truck runs into a fly. Which experiences a greater force? This is a classic. The truck running into a fly. Oh. If you've ever taken a physics class, classic. And people hate the answer. It's always one of those people don't like. Let's say you all. Alright, therefore greater force then?
Oh yeah, it's just because it's the mass of Mars.
So yeah, the
I don't like this.
Wait, actually, no, now you can do.
Like, unless the acceleration is
All right, I'm gonna give y'all a few more seconds. Put what you think.
No way can acceleration.
All right, so 5, 4, 3, 2, 1. All right. I'm going to tell you all the answer, and then even if you got the right answer, it's probably still one of those you're probably not going to like. A lot of people don't like this problem, and yeah, the answer is the same. The answer is the same. And it's a very, like, again, Newton's third law. For every force, there's an equal and opposite force. It's probably something you all might have heard in middle school or high school, and so that might have given you the answer. But look, let's look at the reality. The fly gets decimated. Like, right? We all know that that's the case. So what's up with that? Like, I'm telling you the force is the same. That is the right answer. They both experience the exact same force. But why does one die and the other goes on with its life as if nothing happened? So it has to do with Newton's second law. So let's just kind of write that out. So I'm telling you that their forces are the same. I'm telling you that their forces are the same. Newton's second law said that F equals ma. F equals ma. So let's look at this. You know, 1, let's say, is the truck, and 2 is the fly. So let's just make up numbers. Let's say that the truck is, 10,000 times the mass of the fly. Let's see, a fly is like a gram, maybe. Let's just say it's 1 gram. So a fly has a mass of 1 gram. A truck has a mass of... so a kilogram is 2.2 pounds. That's a useful kind of conversion I know in your head. A truck is what, 3 tons or something? 2 tons, 3 tons, some tons. So that's a ton is 2,000 pounds. So 4,000 pounds, divide that by 2, 2,000 kilograms. Let's just say it's 2,000 kilograms. Okay, so what does that mean as far as the ratio of mass? That means that the mass of the truck is 1, 2, 3, 4, and then 3 more. The mass of the truck is, what is that number? Let's put some commas. 2 million times the mass of the fly. It's 2 million, take the mass of the fly, multiply by 2 million, you got the mass of the truck. Okay, why does this matter? Let's put this number in here. So this says, and I'm actually going to do I want to rearrange this? Let's find that the acceleration of the fly. So the acceleration of the fly, let's just move things around. M1A1 over M2. I just rearrange things. Just rearrange the equation. Mass 1. Yeah, this works out good. All right. So this means if I take this and I put it right here, the acceleration of the fly is 2 million times. Boom, the masses cancel. The acceleration of the fly is 2 million times higher than the truck. And so here's what I want you all to take away from this. It's not force that matters, it's acceleration. I can have a force of 1,000,000 newtons. That doesn't tell you what's going to happen until I tell you what it's acting on. A force of 1,000,000 newtons acting on you is going to kill you because your mass is low. A force of 1,000,000 newtons acting on the earth isn't going to do much to it. Yeah. It's not about force. It's about the acceleration. When you describe what's going to happen to a system, forces are useful only because they let you calculate acceleration. Acceleration is what actually happens. Force is just a tool to calculate acceleration. Yeah.
If you had 2 million flies, would it stop the truck?
It would stop the truck. If you had 2 million flies, which is, don't even, let's make them if you had 2 million flies in the formation of a truck and they hit each other, it would, assuming they were a cohesive unit, they disperse and how they'd react. But 2 million flies hitting a truck, they would stop each other. Well, depending on how fast they're going in momentum. But yeah, so this is the thing that's crazy. People think of forces as acceleration. Forces cause acceleration based on mass. So when it comes to this problem, yes, their forces are the same, but the acceleration is not. That truck is not going to inversely. The truck's going to experience 1 divided by 2 million the acceleration. It's nothing. It's not going to change the truck, but whoo, yeah, that fly's going to accelerate really quickly. If you all accelerate really quickly, you get turned into. There's the Expanse. If you all have seen that show, there's a really good clip in the Expanse of someone that's traveling really, really fast, and then they basically get slowed to nothing instantly, and their body just like jellifies because they go from moving to not moving in an instant, and so therefore their body just like splatters. I mean, they are the fly. That's why things splatter. They're going really fast, and then they're not. Yeah.
You answered my question.
Oh, okay. Yeah, so acceleration is what matters. That's the thing that's really interesting here. That's what Newton discovered. For every force, there's an equal and opposite force. And the example I give is if you punch the wall, it hurts. Because the wall punches back. This is why if you punch someone in the face, their face is made of bone, your hand is made of bone. If you don't punch, I guess there's right ways to punch people, but you can risk breaking your finger bones when you punch someone in the face. If you break their face bones, your finger bones might also break because equal and opposite. You punch their face punches your hand. It's a good reason not to punch someone in the face. It hurts you too, literally, physically it hurts you. If you carry through their, I don't know how to punch someone well, so I'm not going to give advice. But yeah, just don't do it. It's a good idea. Yeah. Yeah, so again, the question is, so the acceleration is just going some velocity to a very different velocity in a very short period. So the change in velocity or change in time, that is acceleration.
Yeah. If you're like, I know my mom's car. It's like an SUV.
Yeah, so acceleration is defined as a change in velocity over time. And I feel really bad. I forgot to do attendance for the second part, and I just realized that someone left, which is very sad. Do you have contact information? Alright, just tell her to email me, because I'm about to do attendance. I feel bad because she was here for most of the time. And we're about to be done, but I totally forgot, and that reminded me. So I'm going to do attendance. This also benefits those that came here late. But I forgot to do it before. It's not to spite that one person. They literally just reminded me. Ooh. So let me do this real quick. And then we'll go back and do that other problem and maybe one more, and then that'll be it. Kind of. Boom. 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 It's a long class. I want to reward you all for being here the entire time. But we're almost there. You all have crammed a bunch of concepts in your head. I'm feeling it, which means you're feeling it. You could try. I don't know how to hold up your cord. I forgot to do this, though. I don't even know if it matters. Whatever. There's a 30-second delay on the stream. I'm just hoping that messes with UCF here.
It does.
Good. That's good to know. So look, I don't have to hide the screen. Huh? Yeah, that sounds like a big... Okay, so that's great. That's what a great system. At least it's streamlined. It's better than the iClickers whose location services fails and then it doesn't let you answer things.
Yeah, like,
I'm not to do that too.
every time they
Oh no!
I know, and I text them. Yeah, I was like,
Yeah.
when I was like failing, it didn't change. Like, Oh, yeah, that makes sense. I don't have as many, but like, it literally be like 19.
Oh. So what I'm gonna do at the end of the year, any of the manual grading stuff, I will do it with like a week. I will do it a week before final grades are submitted.
You did like the day.
Yeah, no, I will do it as soon as I can. So like I'll have to get the final grades because I have to replace the lowest test grade. I have to do that manually. I have to move all the quizzes over. I have to do that man. There's a lot of manual things I have to do that ultimately benefit you all. They're all like, but they're a pain. But I'll send out a thing and I'll fully detail all the things I did. It'll be a fun time. All right, that's long enough. Any other for attendance before it closes? Oh, okay. But just make certain that they contact me. I'll give them attendance for this. I feel really bad. And that's like they stuck around for most of it, so I didn't want to be like, oh, I did it just to get them. No, that's the point. All right. Okay. So here you go. To bring it home. You know, a 2,000 kilogram truck runs into a fly. What experiences a greater acceleration? Yeah, should be a freebie, hopefully. Which one's velocity will change the most? That's acceleration. All right, we'll go for like 15 more seconds. Close it out in 5, 4, 3, 2, 1. All right, how we do? Ah, so good. Yes, this is the one that you were kind of, most people were thinking before. It is the fly. The truck's velocity doesn't change. You hit a fly, your speedometer does not change. You know, like, oh, there's a big swarm of insects. I better hit the gas because I'm about to slow down a bunch. No, you're going the same velocity when you hit a fly. That fly went from, you know, maybe it was just floating in air to going 60 miles per hour in an instant. Yeah, that killed it. That's why getting hit by a truck hurts you. You're not moving, and then a truck hits you, and suddenly you're going 60 miles per hour, 0 to 60. Yeah, that's a lot of force. Yeah, 0 to 60 in like a fraction of a second ain't good for you. Ain't good for your body, because it ain't made to do that. All right. So, free body diagrams now. This is a picture that says we're just going to draw forces on it. Don't worry, I'm honestly going to give you a better, so, you know, it's going to be, woo, look at all these things. I'm going to give you all an example with this. These are fine. This looks rough, doesn't it? All right. So this is the example I'm going to draw, because I'm going to show you all how to draw this. Here's how you draw a free body diagram. You're going to have objects that experience different forces in different directions. So a little bit of, I mean, it's not a living animal, but it's a little sad. It's a stuffed animal. It's a stuffed animal. Nothing is dying in this. This is not a real bear. You got a bear. Let me show you all how you're going to draw a bear in this class. There it is. You know what? Let me show you how to draw a person in this class. There it is. Car. So good. Look, and if you want, you know, that could also be a bear. You just need something. Circle, a block. It doesn't need to be fancy. I tend to draw squares. I don't know why. Draw a circle if you like. It really doesn't matter. And here's the really important part with this. All the forces, you start them from the middle of the object. We're going to draw a bunch of arrows and we're going to start them all from the middle. So in this case, you know, let's just draw them on this picture. So you got a dog pulling it that way, a dog pulling it that way, that way, that way. I'm literally just going to do the exact same thing over here. I draw the dog, it's pulling it that way, that one's that way, that one's that way, that one's down here, And that one's down here. And we'll label these. Let's call this doggo 1, force 2, force 3. It's good to label these vectors because if you want the total force, and this is something I didn't draw on these, I have arrows that point in directions. What do we call arrows that point in directions? Vectors. And guess what happens when we have vectors in multiple dimensions? Can we just add them willy-nilly? No. Guess what we get to do? Break them into the x and y components. So this is just a foreshadowing of what you're going to have to do. So what will this problem actually be? You will find the x, we'll call this f net x. You will find f1x plus f2x plus f3x. And it just goes on and on. That's a 5. I got ahead of myself. f5x. And guess what? We get to do that for y as well. It's so good. We had so much fun doing it in one dimension. Let's do it twice. That should be a 2. Yep. If there was 3 dimensions, I'm not going to make you suffer in 3 dimensions. And then at the very end, Pythagorean's theorem. F net x squared plus f net y squared. Remember, I warned you all, vector addition. Now, will I do like 5 vectors? Probably not, but 2 or 3. If you can do 2 or 3, you can do 5. So I'm not going to like give you all ones where it's just a bunch of math for the sake of math. Remember, up is positive, down is negative, right is positive, left is negative. So when it comes to forces, and this problem, this is effectively, if you all take statics in the future, I keep mentioning statics because many of you have to do it. Net force is 0. So then in that case, the net force is 0, and then you get to do a bunch of things with that. So if this is in this case, if this bear is not accelerating, this whole side equals 0, this whole side 0. So what would a problem look like? A problem would look like maybe I give you F1, 2, 3, and 4, and I say find F5. The bear's not moving. Find it. And so you would find all these components, and you'd solve for that. It'd be so much fun, and it will be so much fun. Statics is an exercise in algebra, from what I've heard. That class, systems of equations. Yeah, that'll be you one day, maybe. Not me. I didn't have to take it. So, anywho, but yeah, free body diagrams. You need to draw these pictures because. What do you have to do with all these vectors? I have to break this one into its x and y. I have to break this one into its x and y. I have to break this one into, if you don't draw the picture, you will make mistakes. You at least have a very high chance of making mistakes. And every time you do a problem, you're rolling the dice. On a test, do things that reduce the chance of making mistakes. Like, it doesn't take that. It is worth the 20 seconds it takes to draw a picture. All right, case in point. A telephone pole has 3 cables pulling on it. So this is let's see, is this the last problem we'll do? Mass versus weight. All right, we're going to do 2 more problems and we'll call it good. We're going to do this one, and then we'll do this one, and then we'll call that good. Okay, so this couple concepts, so we should be done in like 15-ish minutes. Draw a picture. How do you draw the picture? Here's my telephone pole. Looks just like it. Do you know how to draw vectors based on vector notation? 300 I hat, that's 300 in the positive x. 500 j hat, that's 500 in the positive y. This will let you check your work. And then draw the other vectors and find the net force. And if you're stumped, call me on it. Call your own. No, we didn't. We got a box. Which way was that first one? Yeah, the box is the telephone pole. got 3 cables pulling on it. 1, 2. Nice. Yeah, it's good. It's perfect. Yeah. Just be careful on this one. That's gonna get you the wrong answer. Beautiful picture. And I'll give it a little bit longer. The answer is in the problem set. I'll put it up in a second. The first answer, if I put it up too soon, might give too much away. Because the math here is fairly simple for the first part. I'm going to show you all in case you did not draw the picture. Remember, it's always good to draw the picture. So this is my F1. It's 300 on this side, and it's 500 pointed up. We then have a negative 200, so it's a little smaller than that 300. And then we have a negative 800. And this will let you check your work, because what you can do is you can visually add these vectors. You can draw this one, then draw the A2, and then you can draw this. We can actually see what our final vector is pointed at with a picture. That is the benefit of the pictures. It lets you check your work. Your final result should be down and to the right. If your final answer is not down and to the right, that means something went wrong. Being able to check your work is great. And all tip to tail. Being able to add vectors visually is a very useful skill. And you literally just put the vectors one after the other, and then you go from the beginning to the end. Please do practice that skill. All right, put the answer up there. And this problem could have been in our first week's worth of content. It's just adding vectors. The fact that it's forced doesn't actually make any difference in this problem. This is just adding vectors, and the units happen to be newtons for each of the vectors. So it's great extra, like, it's a very important skill. Sorry, I'll go on as we get past. Any questions, comments, concerns? This is the 11th. Yeah, what's up? Yeah, so 1 to 2% is kind of the rule of thumb in this class. If you get within 1 to 2% of my answer, that means your process was correct. And that's where they're all grading on. That's the only purpose of the final answer is to check the process. Okay. So yeah, 1 to 2% is the rule of thumb, because rounding always happens. But it's a good question. Work out the way you want it So as I mentioned, this very much, our givens are kind of here already. It's the forces. We are solving for F net. How do? So this is where I told you all you have to do it in components. So we're going to do F1x plus F2x plus F3x. And then do it for the y, because we had so much fun the first time. There is no shortcuts for this. You just have to do it. And then at the end of the day, eventually, and I wrote this down last time. And this is not an equation on the formula sheet. These are not equations on the formula sheet because this is not a physics equation. This is a math equation. This is break things into x components, add them up. If I am adding vectors, you break into x, add them up. Break them into y's, add them up. Hey, sure, what's up?
To find the direction,
That is what you're going to find. So you'll have the x and y component. You have two sides of the triangle. Yeah. So yeah, this is not, at this point, this problem is actually just a math problem. There is no physics happening in this problem. We chucked newtons at the end of it, but this is adding vectors, which is purely basically math. Now, if I asked you to find the acceleration and I gave you the mass, now it becomes a physics problem. But we have to be able to do the math. Like, there's no getting around this. So F net in the x direction is going to be 300 plus negative 200 plus 0. And then F net in the y is going to be 500 plus 0 plus negative 800. And you get the numbers and, look at that. 300 plus negative 200 is 100. 500 plus negative 800 is negative 300. You do the square root stuff and you get that. The angle. So the angle here. So I drew the vector over here, which is quite convenient. And look at that. It points to the right a little bit. And it points down. So I'm going to actually draw it up here. So if I draw this vector like this, boom, there's that. There's the y component, and this is the net one. The angle. What is the angle? So if this side is 300, and this side is 100, remember we measure angle with respect to the positive x-axis. We measure angle with respect to the positive x-axis. And just to, make that really clear, positive x. All angles are generally measured with respect to that arrow that points to the right. So why is my angle negative? Is this angle above the x-axis or below it? Below it. So when you all find this angle and your calculator, if you put in the positive numbers, they'll give you a positive 71.5. You use the picture and say it's negative because it's below it. All right? So the last step is tangent inverse of, y over x. Okay, a couple last points and we'll look at the last problem and then that'll kind of be it. Y'all are doing great. All right, so real quick question. I'm going to give you all 30 seconds on this. Elon Musk's Roadster on Earth was about 1,250 kilograms. What is its mass now that it's in space? These are actual numbers. If y'all didn't know, he literally put his car on a rocket and shot it into space. So great, it's in space. What's its mass now? Y'all have till 45 seconds. So 20 more seconds. Go with your gut. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, what's the answer? It's the same. Very, very, very important that you do not mix up mass and weight. Mass and weight are not the same thing. All right, sorry, there's one more after, like one last problem after this and we're done. If you mix up mass and weight, you will have problems. Mass is how much stuff something has. If it had this much stuff on Earth, unless it explodes, it has the same mass and space. Great stuff. There it is. Okay, last problem. This one's an important one. A body of mass 2 kilograms is pushed straight upwards by a 25 Newton vertical force. What is its acceleration? And I'm going to give you all 30 seconds to draw the picture. Draw a free body diagram. Look, there it is. Draw a free body diagram of this. Unless it states otherwise, assume every object I give you is on Earth. This problem is not a 2-second problem. So I'm going to give you all 30 seconds, and I'm going to reveal something that many people probably missed on this one. This is very important. This is going to kind of prepare us for the next class. That's why I want to do this last one. Yeah. So we have a force upwards of 25 newtons. It's on Earth. What other force is there? If you forget gravity, and I have both taught you this and I haven't taught you this. What's the Newton's second law? F equals ma. What is the A for gravity? The force of gravity is mg. Ta-da, you all derived the force due to gravity. It's m times g. So, this problem is not just 25 divided by 2. You need to find the net force acting on this object.
Yeah, so basically,
Newton's second law says F net equals ma. F net equals ma. You have 2 forces acting on this. You need to add those forces together to get F net.
F equals ma for this. F equals n.
It was hidden in this problem. It was subtle, but it was not just one force acting on it.
Yeah, you're gonna find your net, so your A here is going to be equal to.
So, this problem, you are going to find, you know, M is 2 kilograms. You know, let's just call this F1 equals 25 newtons.
Do you take into account the normal force with this?
No, it doesn't say it's on the surface.
Okay.
Yeah, there's no normal force because it's not sitting on something. We're assuming this object's in the air. We'll get to normal force next on Thursday. And I'll put the answer.
Wait, why is
Once you get this answer, you're good to go. But do not leave before you get this answer, because if you can't do this problem, Thursday is going to be rough. Like Thursday, we're gonna build on this. This is like the simplest case of a problem we're gonna do on Thursday. So stay here. We're here to help you. Make sure you can do this one. Make sure it makes sense of adding courses, and you'll be better prepared for Thursday. If you just like say, whatever, I'll figure it out Thursday, you will have a hard time. Spend a few seconds now and use the resources that you're available, i.e., me and the TAs. And your some friends around. So A here is not. Yeah, so the other piece that's missing here that I didn't write down, F net equals, you have F1x plus F2x, and you have F1y plus F2y. You actually have to find the net force, and then put that into F equals A. Yeah, it's that problem. It's exactly that problem, and then divide it by this. And that gives you the acceleration.
2,000 times 9.8 because it's kilograms.
Oh, no, kilograms is the base unit. Kilograms is the one weird one where kilograms, it has the prefix, but that's the base unit. Yeah, it's funky, but I didn't make the
Well,
rules.
you don't need to find the net force, right?
And then you had a quick question, and then I'll ping pong around.
I could email you about this later if you prefer to answer that way, but do you have any office hours available on Friday?
I do. So I will be in my office on Friday.
Yeah.
So I'll basically be in there most of the day. Shoot me an email, and I can figure out some time. Yeah, Friday's kind of my flexible day where I can definitely meet people for like 30 minutes or something. I generally have other things I'll end up doing as well, but yeah, I can move it to 30 minutes Friday.
So Thursday, I saw your office hours at 11 a.m.
Yep.
I think it's full, so just after class I can
Yeah, I need to adjust it to like 11:15. I end up being delayed getting there, but yeah, it's right after class. Yeah, I literally go from here to there. I end up after I've talked to whoever and answered any questions. Yeah.
This isn't really like a question. It's just like for the sake of curiosity. Like I was like spinning this.
Oh, sorry.